Hi friends, in this video, let's see question on induction machine. This question only for squirrel cage induction motor. This is not applicable for slip ring induction motor. You know very well. What is the difference between squirrel cage and slip ring? Let's see. A three-phase, four-pole squirrel cage induction motor has 36 stator slots and 28 rotor slots. 36 stator slots and 28 rotor slots. The number of phases in the rotor is. This is a 4-pole machine. We have 36 slots in the stator and 28 slots in the rotor. Then rotor phases is equals to rotor slots by number of poles. Rotor slots by number of poles. This is the formula. You know very well about this. So number of rotor slots are 28 and number of poles are 4. So the answer is 7. So number of phases in the rotor is 7. Number of phases in the rotor is 7. This is generally the question on number of phases in the rotor on squirrel cage. But if they asked you question, what is the number of phases in the stator? If they asked you number of phases in the stator, then some people do like this. Number of phases in the stator is equals to stator slots by number of poles. That is 36 by 4. That is 9. This is 100% wrong answer. Sir, why it is wrong answer? When this is correct answer, this is also correct answer, right? No, sir. This is a three-phase machine. Nothing but the number of slots in the stator, number of phases in the stator is 3 only. Number of phases in the stator is 3 only. But we have a different number of phases in the rotor. The number of phases in the rotor, we have a formula rotor slots by number of poles, but there is no formula for stator phases. The stator phases is the three-phase machine only. So three-phase machine nothing but the stator having 3 phases. Are you okay? Let's see. The power input to a 415 volts, 50 H, 6-pole, 3-phase induction motor running at 975 RPM is 40 kilowatts. Running at 975 RPM is 40 kilowatts. The stator losses are 1 kilowatts. Friction and windage losses are 2 kilowatts. Then the efficiency of the motor is. Let's see here. This is my induction motor. Yeah, its input is 40 kilowatts. And stator losses are 1 kilowatts. When input is 40 kilowatts, stator losses are 1 kilowatt, then the rotor input is 39 kilowatts. Rotor input is 39 kilowatts. Rotor copper losses is equals to, what is the formula for rotor copper losses? We have a formula, rotor copper losses is equals to S into rotor input. Or here we have a rotor output. Rotor output is equals to rotor input minus rotor copper losses. What is the rotor copper losses formula? This is the rotor copper losses formula, S into rotor input. So rotor input into 1 minus S, then we can get the rotor output. What is the rotor input here? Rotor input is the 39,000 into 1 minus S. What is the S? This is a 6-pole machine. So synchronous speed is 1000 RPM and rotor speed is 975 RPM. So what is the slip? Slip is equals to Ns minus Nr by Ns. Ns minus Nr by Ns. Yes or no? 25 by 1000. This is the slip. So here 25 by 1000. So calculate the rotor output. If you calculate rotor output, you get the answer 38,025 watts. The rotor output is 38,000. The rotor output is 38,025 watts. 38,025 watts is the rotor output. Nothing but what is the rotor copper losses? 39 minus 38. Nearly 975 watts is the rotor copper losses because S times of this one. Then 975 added to this one, it goes to 39. Okay, whatever. This is the rotor output, and here they given friction and windage losses are 2 kilowatts. If the friction and windage losses 2 kilowatts, then what is the final output? What is the final output? 38,000 minus 2,000. So 36,025 watts is the final output and 40,000 is the actual input. Now efficiency is equals to output by input. For example, this is taken as 36,000. 36,000 out of 40,000 gets cancelled. 10s are 9s are, so 9 by 10. 9 by 10 is nothing but 0.9 or 90%. 0.9 or 90%. So the efficiency of my induction machine is 90%. Efficiency of my induction machine is 90%. This is very simple question. All the power equations covered here. This is the question on power equations or efficiency. Very important. Okay, understood? A three-phase wound rotor induction motor is to be operated with slip energy in the constant torque mode. When it delivers an output power P naught, delivers output power P naught at slip S. Then theoretically, the maximum power that is available for recovery at the rotor terminals is this is we want, right? So let's see here, the output power is P naught. For example, input power is Pi, and we know that the rotor input, rotor output and rotor copper losses relation. Generally, the recovery at the rotor terminals is nothing but rotor copper losses. How much it is? S times of the rotor input. The recovery power is S times of the rotor input. The recovery power is at the rotor terminals is S times of the rotor input. But here the answers are in terms of rotor outputs. Rotor output answers. But we want in terms of rotor input. Here rotor input is nothing but Pi. Rotor output is nothing but P naught and rotor copper losses. This is the recovery power, that is S times of Pi, but answer should be in terms of outputs. I said you here, rotor input Pi is equals to, what is the formula? Rotor output plus rotor copper losses. From this, rotor output is equals to, what is the formula? Rotor output is equals to rotor input minus rotor copper losses. These are the relations between the power losses. So here I want rotor input to substitute here. What is the rotor input? Output plus losses. Again. Or for example, let's see here, rotor output is equals to rotor input minus S into rotor input rotor output is equals to rotor input minus S into rotor input. Nothing but rotor output is equals to rotor input into 1 minus S. From this, rotor input is equals to, from this, rotor input is equals to rotor output by 1 minus S. Rotor input is equals to rotor output by 1 minus S. You can get this answer from anywhere. Okay, so finally, rotor input is equals to output plus copper losses. Nothing but output is equals to input minus losses. Input is the Pi, copper loss is the S into Pi. So output is equals to this much, input is equals to this much. Now we want the recovery power. Recovery power is nothing but the copper losses. So rotor copper losses is the rotor recovery. So P naught, substitute here, S into Pi. Pi is equals to P naught by 1 minus S. P naught by 1 minus S. So rotor copper losses is equals to S into P naught by 1 minus S. This is the recovery power. Where is the answer? This is my answer. This is my answer. Rotor output into S by 1 minus S is the rotor recovery power. Slip times of the power especially. Right? This is the question on power equations. Right? Let's see here. First of all, stator winding current is DC, rotor winding current is AC. Stator winding current is AC, rotor winding current is DC. Stator winding current is AC, rotor winding current is AC. Stator has a salient pole and rotor has commutators. Rotor has a salient pole and slip rings. Rotor has a salient pole and slip rings, and stator is cylindrical. Both stator and rotor has polyphase windings. DC machine, synchronous machine and induction machine exhibit some of the above properties as given in the following table. Indicate the correct combination from this table. From this table we have to take the correct combination. Let's see first one, DC machine. First one, DC machine. In this DC machine, for DC machine, P and Q statements are correct according to this. Let's check it. P and Q. DC machine, P. Stator winding is DC. Stator winding is DC. Yes or no? In DC machine, stator and rotor. In rotor armature, in stator field winding. Always field winding DC, armature winding AC. This is about DC machine. Let's take it. Stator P. Stator winding is DC, rotor winding is AC. 100% correct answer. Option P for DC. This is for DC. Next, yes. Stator has salient pole and rotor has commutator. 100% correct. Yes or no? In DC machine, rotor having commutator and stator is a salient pole type. So this is correct answer. This is correct answer. But let's check for this. Next, synchronous machine. Synchronous machine. In this synchronous machine, Q. Where is Q? As Q is here. We know that in synchronous machine, stator having armature winding which is AC and rotor having field winding which is DC. Rotor having field winding which is DC. So let's check it here. Q. Stator winding is AC and rotor winding is DC. Very good. This is for synchronous machine only. Next, T. Rotor has salient pole and slip rings. Yeah, in synchronous machine, salient pole. And stator is a cylindrical type. Yes, stator is a cylindrical type and salient poles are there in my rotor. So this is also correct answer for synchronous machine. So this is also correct for synchronous machine. Q and T is possible. Q and T is possible. These two are for DC machine. Next one, induction machine. In induction machine, R. Where is R? R is stator is AC and rotor is AC. Yes. In induction machine, both the winding having AC supply only. Very good. This is for induction machine. Next, U. Both stator and rotor having polyphase winding. Both stator and rotor having polyphase winding. Yeah, 100% correct answer. Both having polyphase. It may be 3 phase, 5 phase, 7 phase. but both having polyphase. So this is also correct answer for induction machine. So with less efforts we completed the question because option A is correct answer. If option B is correct, we have to check all these. It will take time. That's why they given the correct option in option A. So option A is correct answer according to given statements for different machines. Generally, this is the basic concepts. Yes. See this question. See here, a three-phase induction motor is driving a constant torque load at rated voltage and frequency. If both voltage and frequencies are off, what happens here? Voltage and frequencies are off. Following statements related to new condition. Following statements related to new condition. If stator resistance, leakage reactance and core losses ignored. Stator resistance and leakage reactance and core losses ignored already. Then tell me the which of the following statement is correct answer. First see the statements. When voltage and frequencies are off, the difference between ns and actual speed same. The air gap flux remains same. The stator current remains same. The per unit slip remains same. Among the above correct statements are, they given the options. Let's check here. When voltage and frequencies are off, generally ns is equals to 120 f by p. When here voltage and frequency is off and V by F ratio constant, at that condition ns1 minus nr1 is exactly equals to ns2 minus nr2. This is, I said you in concept. We done problems also on this. This is very important. When V by F ratio is constant, then the change in speed is same. ns1 minus nr1 is equals to ns2 minus nr2. This is the first statement is correct only. Next, the air gap flux remains same. Of course, at this condition, voltage and frequency both are off. Hence, the flux density is directly proportional to V by F. Here, voltage off and frequency off. 2 gets cancelled. Again, same flux density. Nothing but the air gap flux also remains the same. And here, stator current also remains same. No doubt at all. First one correct answer, second one correct answer, third one correct answer, and fourth one. The per unit slip remains the same. Is it correct? Per unit slip remains the same. Is it correct? No, it is not correct, because even though ns1 nr1 like this, ns1 minus nr1 by ns1, ns2 minus nr2 by ns2. When these two are same, but these two are not same, ns1 is different from ns2, because when frequency off, ns also off. Nothing but here these two are same, but this is ns1, but this is ns2. For example, this is x, this is x. Nothing but this is x by ns1, but this is x by ns1 by 2. Because when frequency off, synchronous speed also off. So these two are not same. The per unit slips are not same. This is a wrong statement. The per unit slips are not same. But the difference is same and area flux is same, stator current is same. Then which of the following is correct answer? 1, 2, 3 are the correct answer, correct statements. That's why option B is correct answer. Option B is correct answer. This is in generally the question on synchronous speed and slip. A theoretical question, very important concept. Here the per unit slips are not same, because the difference of nothing but the slip speeds are same, but synchronous speeds are not same. Slip speeds are same, but synchronous speeds are not same. Hence the slips also not same. per unit slips also not same. This is the question on theory of synchronous speed. Right? Understood? A single phase induction motor with only main winding excited. Auxiliary winding is not connected to excitation, only main winding excited, would exhibit the following response at synchronous speed. They given that at synchronous speed. At synchronous speed, they given that. And see here, rotor current is 0. No, this is wrong answer. Rotor current is there. This is not 0. And next one, rotor current is non-zero. Okay, but is at slip frequency. Rotor current is non-zero, but this is rotating at 2 times of the supply frequency. 2 times of the supply frequency. This is not equal to slip frequency, because here the main winding is excited, but the auxiliary winding is not connected. That's why here forward flux, forward field is very greater than the backward field. Forward field is very greater than the backward field. And here the rotor is rotating in opposite direction to the actual direction. The rotor is rotating in opposite direction to the magnetic field. That's why here the rotor is rotating at 2 times of the supply frequency. This is not slip frequency. Forward and backward rotating fields are equal. This is also wrong answer. The forward rotating field is more than the backward rotating field. The forward rotating field is very greater than the backward rotating field, because we are excited only main winding, not the auxiliary winding. This is a theory question on single phase induction motor. When the main winding is excited, remember this, the forward rotating field is more than the backward rotating field. Right? See this question. A rotating electrical machine having its self-inductance of both the stator and rotor windings. Both the stator and rotor windings self-inductances. Independent of rotor position will be definitely not developed. Independent of rotor position will be definitely not developed. Which of the following is not developed? Generally, according to this one, generally the self-inductances are independent of rotor position. The self-inductances are independent of rotor position. And especially in this case, the starting torque and synchronizing torque and hysteresis torque all will produce, but reluctance torque will not develop, because generally the reluctance torque aligns the rotor and stator in minimum reluctance position. It aligns the rotor and stator in minimum reluctance position. Minimum reluctance position. Generally, in our induction machine, there is no minimum reluctance position. Hence, there is no developing of reluctance torque. This is independent of rotor position, the self-inductances, and there is no minimum reluctance position here. That's why there is no reluctance torque production in this machine. So here, the position will be definitely not develop the reluctance torque. Definitely not develops the reluctance torque. This is a theory question again, right? Very important question and expected question for every GATE exam. Every competitive exam, this is the expected question. Listen carefully. A single phase 230 volts 50 Hz 4-pole capacitor start induction motor has the following standstill impedances. Main winding impedance they given, auxiliary winding impedance also given, the value of the starting capacitor required to produce 90 degrees phase difference between the currents in the main winding and auxiliary windings will be how much capacitance we required to get the 90 degrees phase difference. Once see here, for example, this is a capacitor start induction motor, right? This is my main winding and this is my auxiliary winding. Here capacitor is connected because this is a capacitor start winding. And here we are applying 230 volts 50 hertz supply source. This is the main winding and this is the auxiliary winding and this is the capacitor C and this is the centrifugal switch. And main winding impedance they given Zm is equals to 6 plus J4. Auxiliary winding impedance also given 8 plus J6 they given. Now take the vector diagram for this. This is voltage V. This V is common for both because these are in parallel. And here the current is Im. This Im is lagging. This Im is lagging to the voltage because pure inductor. And this is the auxiliary winding current Ia. Actually, this Ia leading to the voltage because this is capacitor. Xc is greater than Xa. Xc is greater than Xa. So here this is in leading load. Now, if this angle is 90 degrees, what is this Xc? What is this Xc? Not only Xc, not they asked Xc, they asked C. What is the capacitance we have to add to get 90 degrees between them? For example, this is theta m, this is theta a. Theta m plus theta a should be equals to 90 degrees. What is theta m? Theta m is the tan inverse of xm by rm plus theta a is the tan inverse of xc minus xa by RA. XC minus XA by RA. Then only 90 degrees is possible. This should be equals to 90 degrees. Tan inverse of A plus tan inverse of B. Tan inverse of A plus tan inverse of B. Tan inverse of A plus B. A plus B. Sorry, A plus B. Tan inverse of A plus B by 1 minus AB. Tan inverse of A plus B by 1 minus AB is equals to 90 degrees. Bring this tan inverse in this side. Bring this tan inverse in this side. So tan inverse of 90, tan 90. Tan 90 nothing but infinite, nothing but 1 by 0. 1 by 0. If you calculate this cross multiplication and find the xc from this, we can get xc is equals to from this xa plus ra rm by xm. This is the formula you should remember and don't do all these calculations again in your exam. You have to substitute all the values here. That is very difficult to solve it. That's why I simplified this equation. The simplified equation is xc is equals to xa plus ra rm by xm. This is the capacitance required to get the 90 degrees. So tell me, what is xc value from the equation? xa is the 6 plus ra is the 8 multiplied with rm, main winding resistance and main winding reactance. So the answer is 6 plus 12, 18 ohms. Be careful. This is the 18 ohms is the capacitive reactance we required here. But what we want, according to question, what we want, the capacitor required. How much capacitor required? We know XC is equals to 1 by omega C. C is equals to 1 by XC, 1 by 2 pi F and XC. XC is the 18. If you calculate this one, you can get the answer 176.84 microfarads. 176.84 microfarads. Option A is the correct answer. Option A is the correct answer. What is that? XC is equal to 1 by 2 pi FC. 2 pi FC, I want this C. So C is equal to 1 by 2 pi XC. XC 18 and frequency 50. And if you solve this, you will get the answer 176.84 microfarads. 176.84 microfarads. Option A is 100% correct answer. This is very important question. We must expect it. This is the expected question again and again in every competitive exams. Right? So this is the question. You should remember this formula, shortcut formula. Directly you can get the answer. XC, the capacitance required to get the 90 degrees is equals to XA plus RA by XM. RA by XM. By solving this equation, by cross multiplication. Right? Understood? A 400 volts, 15 kilowatts, 4 pole, 50 Hz star connected induction motor has full load slip of 4%. Full load slip of 4%. The output torque of the machine at full load. Output torque of the machine at full load. Very simple question. We know P is equals to 2 pi nt upon 60. From this, torque T is equals to 60 upon 2 pi, 60 upon 2 pi, and P upon N. What is N? First of all, synchronous speed. For 50 Hz 6 pole, synchronous speed is 1500 RPM. Yes or no? Yes or no? So, 4 pole 50 Hz. 4 pole 50 Hz. The synchronous speed is 1500 RPM. Right. Next one. What is the slip they given? The slip is 4%. What is the rotor speed? NR is equals to NS into 1 minus S. 1500 into 1 minus 4%. You will get 4%. 4% nothing but 1440 RPM will come. 1440 is the N. And P and 6 where everything is there. Let's substitute here. 60 upon 2 pi, 15,000. They given 15 kilowatts upon 1440. This is our answer. So if you calculate this answer, you will get that answer is around 99.47 Newton meters. 99.47 Newton meters is the correct answer. Very simple question. A basic formula P is equals to 2 pi nt by 60. Here we have to apply this formula and the NR value 1440 RPM. This is the question on speed equations of induction machine. From that torque, we have to find out the torque. Is it okay? Understood? Under no load condition, if the applied voltage to induction motor is reduced from the rated voltage to half the rated value. What happens are here? Rated voltage to half the rated value. Then what happens? Speed decreases and stator current increases. Both the speed and stator current decreases. Speed and stator current remains same. There is a negligible change in speed, but stator current decreases. Which of the following is correct answer? See here, under no load condition, generally the torque T is equals to K V square S R2 upon R2 square plus S square X2 square. R2 square plus S square X2 square. Of course, here if S square X2 square neglected, what is the answer? kv square S upon R2, because R2 square R2 gets cancelled. Here the voltage and slips are, here the slip is inversely proportional to V square. Slip is inversely proportional to V square. Here K constant and there is no change in rotor resistance. There is no change in rotor resistance. K constant. Here the changing is voltage and the slip. How they will change? Slip is inversely proportional to V square. If voltage is halved, if voltage reduced to half, then the slip is increased because of square formula. Here slip increased by 4 times. Here slip increased by 4 times. When slip increased by 4 times, then automatically speed decreases. Speed decreases. When slip increases, speed decreases. So which of the following is correct answer? Here speed remains the same. Wrong answer. Here there is a negligible change in speed. Wrong answer. There is a lot of change in speed. Both speed and stator current decreases. Speed decreases and stator current increases. Let's see here. Here the torque should be constant. Here voltage decreases. At this condition, the machine draws the slightly more stator current. Slightly more stator current. At this condition, the stator current increased. At this condition, automatically, when voltage decreases here, the stator current slightly increases. So the answer is the speed decreases and stator current increases. Speed decreases and stator current increases to tackle the torque actually here. In generally, when voltage is decreases here, the stator current increases. Like that, option A is correct answer. Here slip increasing. Slip increasing. So the speed decreases and the stator current increases. This is the question again, a theory question on induction motor. Are you okay? Understood? Thank you, sir.